And it's no surprise that I'm going to talk a little bit about clouds and the link to cosmic rays. Let me give you a sort of overview of what I'm going to talk about. I have two parts. The first is to give you a background of why I think cosmic rays are important and how they link to cloud. We have some experimental evidence, we have observational evidence, and I will talk about what can the link be between ionization in the atmosphere and then the formation of clouds. The last part will actually be on a field that was initiated by NEAR. It has to do with changes in climate over millions of years. It's very interesting because it's completely independent of solar activity. Here you see more or less the idea which NEAR also was presenting, that we have cosmic rays, which are particles that comes from space, and they are mainly produced in stellar processes where we have supernovas and they make a shock front, and that accelerate particles to very, very high energies. And these particles, they shower in over the Earth. And there are two things that can modulate the cosmic rays. One is solar activity. It's on the order of 10%. And the other, which I'm going to talk about in the last part of the talk, is that you can have changes on the order of 100%. So when I started this, I knew that people have been finding correlations between solar activity and climate. And the question I asked me was, if it's going to work, it might actually be clouds that are affected by cosmic rays. That was sort of the fundamental idea. And when I found data, here you see data from 83 until 2005. The blue curve is actually from a satellite data set of low clouds, and you see this nice correlation. The red curve here is the changes in cosmic rays over the same period. So it gave an impression that maybe there's something interesting going on, but of course this is just a correlation, so there's no guarantee that there is a physical mechanism. And at the time when we presented this, many people were saying that there's no known mechanism, so we actually don't believe that this can be right. It could be some accidental correlation. And I should also say that the changes in cloud cover observed from satellites is very, very difficult. It's very, very difficult to maintain a calibrated system. So you might end up where the correlation actually breaks down, and you cannot be sure what is the cause of it. So there's no guarantee that this is necessarily, a causality that we have between the two curves. As NEAR showed, the effect of solar activity over 11 years is of the order of 1 to 1.5 watt per square meter. So over the 11 years. And the changes I just show you in cloud cover, they are actually of the order that fits within this picture. So it could be that the clouds are the amplifying mechanism that makes solar activity so important in our climate. So the obvious question is, how do cosmic rays affect climate? And the idea is that you have to understand how clouds are formed. And in order to have a cloud, you need what we call cloud condensation nuclei. These are very small aerosol particles. They have a certain size on the order of 50 to 100 nanometer. And at that size, water vapor can condense on them and they can become cloud droplets. The fundamental question is then, how are these small cloud condensation nuclei formed? And it turns out that a large fraction of the cloud condensation nuclei are actually formed directly in the atmosphere from gases. So you have molecules in a gas, and then they can stick together and make a small cluster. And this cluster might be stable, and you have a small aerosol, and then subsequently it grows by condensing more gas, and finally it becomes a cloud condensation. It becomes a cloud droplet. So the idea that we had was that this ionization from cosmic rays that is happening in the atmosphere all the time, it actually promotes the stability and the formation of these small particles. That was the fundamental idea. Now, here you actually see a very good example of what happens if you change the number of aerosols that goes into the atmosphere. Here you have a region over the oceans with low clouds, and these stripes here are actually ship tracks. So what is happening is that a ship from the engine is pumping out a lot of aerosols. These aerosols goes into the clouds, and you all of a sudden get condensation of water vapor, but you see that you change the microphysics along the track of the ship. And the idea is that if you can do this systematically, I mean, if solar activity is capable of changing the number of aerosols or the aerosol properties, it will be a very effective way of changing the radioactive properties of the Earth, of clouds, and so on. So that was the idea, and the initial thing we did was that we could test these things experimentally. We could test whether small ions actually promote the formation of small aerosols, okay? And this has actually been measured, and I think this is the measurements we did. This is from 2006 when we first published it. It came out 2007. Nonetheless, what you have along this axis is something that corresponds to the ionization or the cosmic rays. And when you increase the cosmic rays, you increase the number of, or the formation of small particles in our experimental chamber. And in 2011, the Cloud project actually came up with the same or similar results, showing that when you increase the ionization in a chamber, you are producing small aerosols. So we have a production of aerosols. So that, you can say that was very supportive of the theory, but it is extremely important that these small particles, that they grow to cloud condensation nuclei, and if they don't do that, they will not affect climate. And it turns out that there was a number of groups that put this mechanism into large models, climate models, and tested what happened if they increased the number of small cloud condensation nuclei as the solar activity changed. So they are sort of testing the idea, and it turns out in all of these simulations, even though they put in extra of these small particles, more or less none of them grow to cloud condensation nuclei. And that was seen as a fundamental problem for the whole idea. It was said many places that that was the end of this idea, but fortunately we can also test it in the laboratory. So the important thing is that modeling says no to this effect on ions on cloud condensation nuclei, and therefore there's no link, or it's not important. But we could actually address it in our laboratory. So what we did was the following. We had our cloud chamber here. We could shine UV light, which corresponds to the effect of the sun. And then we can put in various gases. And when we had this light, we are producing small aerosols all the time. Then we can add ionization from these radioactive sources, which is like turning up and down the cosmic rays, and then we can measure what is going on. And this is a picture of the chamber. It's about 8 cubic meters large. You can see the radioactive sources here and here. Okay, but here you see a typical experiment where we are shining light in on this part of the chamber, producing small aerosols, and they are growing, and we have the size of the particles going up this way, and this is the number of particles, and they go into a steady state. And then we can sort of add some extra particles by different methods, and then we can see what is the fate of having additional small particles. Will they grow to cloud condensation nuclei? That is the fundamental question. And the first experiment we did was to add neutral particles to our chamber, very small particles on the order of 3 to 5 nanometers. And here you see the result. Here you have the size. This is about 10 nanometers and this is 70 nanometers. At this size they are cloud condensation nuclei, so they are large enough. And what we do is we increase the number of particles with about 50%. And then you see as they grow, fewer and fewer of them actually makes it to cloud condensation nuclei. So when we add neutral aerosols and we are not using cosmic rays, the result is in complete agreement with the numerical modeling. And the reason is that when we put in more particles, we have more particles competing for the same gas that they have to grow from, and then they grow slower, and there's a larger chance that they get lost by some process. But then look what happens if we do it with cosmic rays. If we add cosmic rays to the chamber, we produce about 15% more small particles, but notice that nearly all of them grow to cloud condensation nuclei. And that is in complete contradiction of all these modeling results. So something is going on which is not in any of the physics of all these models. And this could very well be the reason why this mechanism actually might work in the real world. However, people were telling us that maybe we have a mechanism that works in our laboratory, but if you go out to the real atmosphere, it might not work. There are so many other processes that are producing cloud condensation nuclei, so therefore it need not to be important. There are so many other processes, so it will just drown. So what we did was to look at what we called natural experiments that the sun is providing us. We have these coronal mass ejections where you have a large piece of plasma that comes out. If you imagine the sun here and you have this plasma, if it hits, if the Earth is here, for instance, and it hits the right way, then there is a sudden drop in the cosmic rays. That means that when these effects are happening, we can use it to test whether there is an effect on clouds and other parameters relevant for these ideas. And here you see the result. This is the red curve here